And ranch.
And ranch eggs.
Did you just bite into your apple?
Yeah, just
sound effect. You know I'm right.
that'll enhance it.
This episode brought to you by McDonald's.
Did you just
I keep on trying. Just don't worry about it.
Because Vaughn is like kind of flipping out over there.
That's because Vaughn is Vaughn.
We're good?
Subtracting class.
No, I didn't punch her.
Hey, Vaughn, there's bowling reports in the office.
I'll be a witness.
Okay.
Michael is most trustworthy. Who holds the door for him?
Okay.
Who's trustworthy of his word?
Word. So today is brought to you by the letter and concept of work. Okay? We're literally doing work. So that's what we're doing.
Oh, yeah.
So, sorry. So here's what we have left. We have one like kind of big unit on working energy. And then we'll have a test on that, and then we'll have like some odds and ends stuff like on thermodynamics and gas laws and that type of buoyancy. And then we're basically done. So for those of you that really want to plan ahead, here's how your last week in this class will be, those last 5 days. So on that Monday, we'll review for the written final, which is going to be on Tuesday. And that written final is going to be all multiple choice, and it's going to be comprehensive from day one. Now don't flip out and go, oh my God, it's comprehensive. Okay, look, what did we talk about the very first day? Meters, kilograms, seconds, forces, velocity, acceleration. Gee, we haven't talked about those since the first day. So don't flip out on the fact that it's comprehensive. It's okay. You can have your equation sheet. It's not a big deal. So that'll be Monday. We'll review Tuesday. That's going to happen. And then you're going to have a 3-day lab final, which is Wednesday, Thursday, Friday. Okay. Now I'm going to tell you all right now. So if you want to begin to plan the dynamic, there are no more than 4 people in a group. Okay. So I'm just telling you now, there's no more than 4 people in a group. So you don't have to decide groups right now, but I'm just telling you, there's going to be no more than 4. Okay. Maybe a group of 5, maybe, but I doubt it. Okay. So here's the other thing that I'm going to tell you. That lab report, your lab final, and everything you have to hand in is due at the end of the block on that Friday. Not after school, okay? Not halfway through 4th block. When the bell rings at the end of 3rd block, you have to hand in whatever you have, okay? Now, don't flip out. You can easily get done. But I'm just telling you, I'm just going to plant the seed right now. It is due at the end of that block, okay? So just telling you right now. Okay. And then prior to that, we'll have like tests over energy and probably we'll see how it plays out. Because basically after this week, we only have like 2 weeks, and then we've got that week of kind of that final. So we don't have all that much time left. All right. So from a physics perspective, work is a simple calculation, but yet it's also complicated. So work itself is just force through a distance. Now, there's 2 components that are important to this. The force has to be exerted, and it has to move in the direction of the force. Okay? So here's as simple as something gets. So let's take, I take 1 kilogram mass, and I push it across the desk, and I push it for a half meter. Okay? Simple as that. So if that's the case, I would take, let's say it took 3 newtons to push it, and I pushed it for a half a meter, so I would get 1.5. Now, from a units perspective, one option is you could say, oh, that's Newton meters, okay? And that's cool, okay? Now, but here's where this gets a little bit confusing, because they're not the same thing, but they're kind of related. So remember we talked about force, and torque was force times radius, and that is in Newton meters, okay? So torque and work are somewhat related, but they're not, certainly not the same thing. So to kind of clean this up a little bit, and you'll see that work is also a measure of a change in energy. Does anybody know, for those of you that have been through Chem 2, what's the unit of energy that we use in science?
Joules.
Joules. Now, let's make sure that we know which type of joule we're talking about here. Okay? This kind, okay, named after Prescott Joule, right? Not the kind that, as my fourth block is noted, why do they have bathroom stalls in the Joule room? So, yeah.
Was that Joel? Did Joel say that?
That was Joe Gaddy.
Yep. Yep.
Yeah. That was why do they have bathroom stalls in the Joule room? Anyway, so this is named after Prescott Joule. He did his work and he was very popular in high school because his family owned a brewery, and he was a British scientist and basically didn't have anything else to do. So he looked at the relationship between thermal energy and mechanical motion. And you kind of all intuitively understand this. So like if I've got this container of Coke, right, and it's got some ice in it, I just let it sit there, okay, eventually it's going to melt. But what if I sat here and continuously shook that thing around?
It's going to melt faster.
It's going to melt faster. Why?
There's more energy. Some more.
Yeah, now you have kinetic energy, okay, the stuff is moving around. And so he was the first one to really quantify that relationship between mechanical energy and thermal energy. And so this is why, if you look at energy as far as like an overarching theme, energy is the overarching theme that ties together all branches of science no matter what. Whether it's chemistry, physics, biology, geology, doesn't make any difference. Energy is the one thing that unites all the branches of science, and no matter what, it's all going to be measured in joules. Okay, so if you understand that, and you'll understand that a whole bunch of different random things kind of all fit together. Okay, so you can say 1.5 Newton meters. Typically, we're also going to call that 1.5 joules. Okay, so that's as simple as it gets, right? Hey, I pushed a block. Here was the force. Here we go. Now, the other thing that's complicated about work is that it's all about the signs and it's all about the prepositions, okay? So you usually talk about work being done on an object or work being done by someone. So I could say, okay, hey, I'm doing work on this 1.5 kilogram mass by pushing it a certain distance. So, and this is on the lecture notes, but here's the general rule on sign for work. If the force is in the direction of motion, or you lift something up, or you make it go faster, work is positive. If it's slowing it down, if it's lowering it, or it's in the opposite direction of motion, work is defined as being negative. Okay? So there isn't like a quantitative way to, oh, this is how you calculate it. You just have to look at it in the context of the problem. So let's kind of step back a little bit in terms of how thermal energy plays into this. So let's say it's cold outside and you've lost your mittens, okay? And your hands are cold. What are you going to do? Rub them like this. Now, when you do this, are you doing work? Why?
Yes.
Yes, because you're applying a force in the direction.
Yeah, you're applying a force over a distance, right? You're doing work. Now, if you do this, guess what? Your hands aren't going to warm up. You're just going to look like an idiot, okay? But if you actually push them together, okay, you're doing work because of the fact that you're exerting a force through a distance. And that frictional force is generating thermal energy. Now, if your hands are frictionless when you do that, what would happen?
No energy would be produced.
Yeah, because there's no friction involved. So anytime you take this and I push this across, there's a certain amount of thermal energy that's generated because of the fact there's friction. Now, I don't have to worry about the table catching on fire when I push the 1 kilogram mass across it. But if you've ever seen any of the survival shows, okay, Bear Grylls, for example, how do they start a fire? They do this, right? Okay, with the stick. And they push down. Are they doing work?
Yes.
Yeah.
Yes. What are they generating?
Heat.
Heat. Now, why don't they just kind of go, you know, if you've ever seen them, it's just like hardcore cardio, right?
Not a lot of.
So, yes. So, why? Why do they go so fast?
Because there's
generate more heat, because if you go slowly, the heat gets dissipated, okay? So if you do that very, very quickly, you generate a tremendous amount of heat that you can keep confined within a small system. So that's what they're doing. From a physics perspective, they're going, oh, they're doing work. They are translating mechanical energy, mechanical work, into thermal energy, and voila. You get fire. Okay, or you can do the flint thing where you strike the rocks and you get a spark that comes off. But the sticks are much more kind of primordial. Okay, so friction generates thermal energy. Okay, that's the point of the story. Friction generates thermal energy. So if I look at that 1 kilogram mass, okay, sitting here, and let's say that I was pushing with a force of 3 newtons, right? So that's my force applied. So here's the deal. Are there any other forces, in the 1 kilogram mass, are there any other forces acting on the system?
Force.
Gravity, which had the value of what?
Negative.
It's a 1 kilogram mass.
Negative 9.8.
Negative 9.8 newtons.
You got your force normal.
Force friction. Okay, so that got gravity pulling down. I got my normal force, which is going to be
9.8.
9.8 newtons. Now, assuming that I'm pushing it at a constant velocity, what else is there?
Force friction.
Friction, which is going to be acting
Opposite.
with a value of negative 3 newtons. So a lot of times when you're talking about work calculations, you want to talk about the work that's done in overcoming friction. Okay? So if I push this thing a half meter, then the work done in overcoming friction, all I'm going to do is I'm going to take that frictional force, which is negative 3 newtons, multiply that by the distance of a half meter, and I would get negative 1.5 joules. And I make that negative because it's in the opposite direction. This is also how much thermal energy would be generated by pushing that block. Okay? Now, what if this was the magic frictionless 1 kilogram mass? I'd have to do a little bit of work to give it a push to get it to move, right? But if that was the magic frictionless 1 kilogram mass, would I have to keep applying a force to keep it moving?
No.
No. So if that's the case, I wouldn't do any work because to keep it moving. I'd do a little bit of work to push it, but that would be it. Okay? So if it's frictionless, I don't do any work. So here's what you have to consider. When you're looking at work calculations, listen to me very, very carefully. The only force that you consider is in the direction of motion. Now, why don't I take this negative 9.8 newtons times a half meter?
Because it's not moving down.
Yeah, it's not moving down. I'm not going to worry about my normal force, because guess what? It's not moving up. Okay? Now, I worry about my frictional force because it's parallel with it, and it's in the opposite direction of that motion. Okay? So, any forces only count in the direction of motion. Okay? Listen to me. The only forces that count are in the direction of motion. Now, what if I take this 1 kilogram mass and I lift it up to a height of 1 meter? Would I do work in that situation?
Yes.
Why?
Because you're using a force to push.
Yeah, I'm exerting a force and it's moving in that direction. So if I take a 1 kilogram mass, okay, if I take that 1 kilogram mass times G, I get 9.8 newtons. Multiply that by 1 meter, I'm going to do 9.8 joules of work to lift it up. Now, you'll also see that this is completely tied in with energy. Okay, and one of the types of energy that we're going to talk about is gravitational potential energy, which is MGH. So, if I lift something up, I'm doing positive work because I'm increasing that potential energy. Now, what if I take that 1 kilogram mass and I just hold it up here? If I hold it here, Bree, am I doing any work? Why not? My arm's getting tired.
All you have is force.
All I have is force. What do I not have? I don't have a distance. I'm not moving in the direction of the force. So by just holding it up here, I'm not doing any work because the force is pointing this way, but it isn't moving that way. But now if I take it to lift it up there, I do work. But holding it there, I don't do any work. Okay? So if you're lifting something up, and this is on the lecture notes, if there's ever a sheet of lecture notes that you read, this would be it. So I'm going to lift that thing up. I would do 9.8 joules of work. Now, if I lower it down, and I'm decreasing that potential energy, I would do the same amount of work, but then it would be negative. Okay? Now, can gravity do work?
Yes. Yeah.
Why, Honest?
Well, if you're in free fall, it's a force that's causing you to move a certain distance.
Yeah, so if I hold this 1 kilogram mass up and I drop it, gravity's doing that work. Okay? Now, if I lower it with my hand, I'm actually working against gravity, because if you think about lowering something down, even though you're lowering it down, you still have to exert an upward force to keep it from falling. Okay? So, here's your general guidelines. If you lift something up, or it's in the direction of motion, that's positive work. Okay? Simple as that. Don't make it complicated. If it's in the opposite direction of motion, you're not doing any work at all. Your friction's doing work, but that's going to be a negative value. Now, what if I did this? What if I take this 1 kilogram mass, and here's the caveat. Once I get it moving, okay? Once I get it moving. So once I get it moving like this, am I doing any work? Nick, once I get it moving and I'm walking it across like this, am I doing any work at all?
No,
Why not?
because you're not actually like moving the object, you're just kind of going with it.
I'm not moving the object.
Well, you're not applying a force on it.
Yes, I am. Because if I don't apply a force, what's this thing going to do?
Following.
It's going to fall.
You are.
You're not applying the force in the direction it's moving.
Okay, that's what you were missing. So, if I'm walking this way, okay, and this is the whole key, once I get it moving, what's the direction of the force? Up. But which direction is it moving? Moving it that way. So I'm not doing any work. Now, if I walk and I lift it up at the same time, then I'd be doing work. Because then it's going to be moving in the direction of the force that I'm applying. So, if you just carry something, it sounds odd, but you're not doing any work. Okay? Because now, if you lift it up, hey, then you're doing work. Got that idea. Now, the other thing that you see, that's kind of cool, is that work is also going to be equal to a change in energy, okay? And that could be potential energy, it could be gravitational potential energy, it could be kinetic energy, a whole bunch of different things. So work in a generic way is also a change in energy. So if I take Gary the golf ball, okay, and I'm going to throw this to Shively, right? So I'm going to throw Gary the golf ball to Shively. Did I do work? Yeah. Olivia, did I do work?
Yes.
Why?
Because you used a force to move it over distance.
Okay, I applied a force over distance, right? Beautiful. So you'll see, especially tomorrow, that kinetic energy is 1/2 mv squared. So when I applied a force, what did I change? I changed the velocity. By changing the velocity, I changed the amount of kinetic energy. Okay? So the amount of kinetic energy that I change is going to be equal to the work. Now, if I just apply a little bit of force over a short distance, I'm not going to change the energy of that golf ball very much, because I don't exert much of a force, nor do I exert much of a distance, right? Now, I wouldn't do this because I like Shively, especially at this range. I'm not going to stand here and wind up, and throw that golf ball at him as hard as I can. Okay? Rude, right? But I would greatly increase the amount of kinetic energy of the golf ball because I applied a much bigger force over a much greater distance. Okay? Now, did Shively do work on the ball?
Yeah.
Why?
He's applying a force. He's doing it in the opposite direction of the movement, so it has to be negative.
Yes. But he would do work, and Grape had a good point. His work would be a negative value because of the fact that his force is in the opposite direction of the ball. I would do positive work because I made it speed up. He would do negative work because he made it slow down. Now, what if you don't exert a force? Are you going to change the kinetic energy of the ball? So throw that back, okay? So if you don't, just hit my shoulder, aim for the hand. So if I don't catch it, okay, then does the kinetic energy change? No, because without a force, what do you not change?
Velocity or
Yeah, if you don't change the velocity, you don't change the kinetic energy. Okay? So that's why work and changing kinetic energy are so closely tied together. Now, let's look at a different situation. So I'm going to take the rubber stopper and get that going around like this. Now, once I get it up to speed, okay, this is the whole key. Once I get it up to speed, is work being done on the stopper?
No, because there's a force, but it's not in the direction of motion.
That's part of it. What'd you say?
There's a force, but it's not in the direction of motion.
Yeah. So here's the deal. When that rubber stopper is being swung around, okay, what's the direction of the force? Did someone say outward?
the rubber stopper's going out, is what I mean.
Okay.
No, you can. I swear.
Okay.
I'm not confused.
Oh, no, I'm good. I'm with you, honey. So the force itself is inward, right? So that force acting inward, so here's the question. If you mark a certain position, okay, it's out here, later on, is that position going to change based upon that force? No, that's going to stay a fixed distance. So that's like me holding up this 1 kilogram mass. If I just hold out this 1 kilogram mass, I'm not doing any work.
Your arm's gonna grow.
Wait, what?
What?
You're gonna get big.
That's
It's gonna be a
biology.
workout after a while.
Oh, so when I get that tat.
Yes.
Yeah.
It's like make it do a little dance.
Where's my desk? It's over there. Okay. Grow a beard, you know, start wearing like short sleeve shirts, you know.
Like with the. Like
I'd be
the
so
bike.
proud.
Oh, yeah, yeah.
Even
Or
birds?
better yet, go with the old school, like roll the cigarette
cigarette,
on the
yeah.
sleeve. Yeah.
Wait, is that in the contract with which your brother has to kill you if you get a tattoo?
No, we've never discussed it. I
What
think
about-
my father will come back from the grave and
What about
possibly
pink
haunt me.
tights?
But
It's worth it.
the pink tights, that's just it. My brother might, if my brother kills me, it's all on you. Okay?
On me
I will
specifically.
avenge your
Not
death.
you for making
No.
the deal.
I will avenge your death just like Hamlet.
Are you going to say that you're going to
Stanley.
kill me or kill?
Did you ask her about that?
I did.
What'd she
showed up.
say?
She's like, yeah, apparently the kids have deemed it Stamlet. Or Stanley, or whatever it's called.
Did she show it to you?
She just shows the cover.
Oh, okay. Yeah, it's funny.
Are you saying you're going to kill me?
Oh,
his
I'll kill the
brother.
person who killed him.
Okay, because he said that his death was on me.
You're like Hamlet's wife.
He said that his death was on me.
Because you
Hamlet
brought
Senior
up
does.
pink
Yeah,
tights.
because hey,
Ah,
we brought that. Why did we? Whatever. It's fine. It doesn't.
I think it was because it was
okay,
that
get over there.
It wasn't.
What
My,
did I do?
it
So-
wasn't my fault.
it was
though.
Eli.
It was. Shh. Sorry. Not my fault. That's all I gotta say.
So, if you're going around in a circle, you're not doing any work. Now, what if I did this?
Yeah, because it's going in the direction of the force.
Then you do work. Why?
It's going in the direction of the force.
Yes. Then it's moving in the direction of that force. Okay? Now, if I reverse it, Then what?
It's going in the opposite direction of force, so it's
Yeah, so
still.
then you'd basically be doing like negative work, okay? But as long as that radius stays constant, now, what if you're in an elliptical orbit? Then would work be done?
Yes,
Yes.
Yes. Why?
because the radius isn't constant in an elliptical orbit.
Radius is a constant. Nicely done, Matthew.
Thanks.
Okay.
Try to use this.
Now, let's say hypothetically, you all decide to finally go off to college next August, and you're going to borrow somebody's truck.
McDonald's University.
Huh?
McDonald's University.
Okay.
In Chicago, it's real.
Dude, I'm going to like.
Is it real?
Yes.
It is an actual thing.
The electoral
Coastal
college.
University.
Yeah.
That's, yeah, you deserve to be in there.
So let's say that you've got a fridge
Big scholar.
that has a
Hold on,
mass
hold on.
of
Victoria.
Yeah, I'm on side.
10 kilograms, right? Okay, you've got a mass of 10 kilograms. And the tailgate is 1 meter high. And you need to get that up onto the tailgate. So you grab a hold of it, you go, "Hoo-ah!" Okay, and you set it up there. So this is 1 meter, and this is 10 kilograms. How much work would you do in lifting that up? 10 kilograms, 1 meter. 10 joules?
98 joules, right?
Well, does mass even
Yeah.
factor into it? It's just force and distance, so wouldn't it just be 9.8?
Yeah. What?
So I've heard 10.
It's, but
What's
it's,
the force?
it's 90, mass does factor into it, because you need the gravitational force.
But so these.
Negative 98.
Because it's the gravitational force.
Yeah.
So it's 98,
Positive
it's 98
Positive
Newton meters.
Okay,
98 joules.
so why isn't it just
Yeah.
10 kilograms times 1 meter?
You need the frictional
It's
force.
not mass times distance.
It isn't mass times distance, it's
Force
force times
Oh,
distance.
sorry, gravitational force. Sorry, I said frictional, meant gravitational.
Yes. So, how much gravitational force do you have to overcome?
98.
Yeah, that's going to be 98 newtons. So if I take 98 newtons and I lift it 1 meter, I would do 98 joules of work. Go with that. Okay, simple calculation. Well, let's say you look at this and you go, man, 98 newtons, not feeling it. Can't do 98. It's over the top. So what could I do to lower the amount of force that I have to apply?
Decrease friction.
Oh, ramp! Oh, simple machines. Y'all learned about that like middle school?
Seventh grade.
7th grade, back when you all were cool. Yeah.
That has not changed.
Thank God I didn't teach you all middle school.
That class is loaded.
Can you imagine me teaching middle school?
Hey, freshman.
Actually, I did my student teaching at Fort Riley Junior High. Swear to God, I'd never set foot in middle school again. Oh, it's horrible. Okay. So let's say that you got a 30-degree ramp. This is 1 meter, and this makes this ramp 2 meters long. Okay? And not only is it a cool ramp, it's the magic frictionless ramp.
Oh.
Okay? So it's the magic frictionless ramp. Assuming that the ramp is frictionless, okay? Listen to me very carefully. Assuming that the ramp is frictionless, would I do more work, less work, or the same amount of work as opposed to just lifting it straight up?
Less.
Same amount.
More.
It's the same.
I've heard more, I've heard less, I've heard same.
If it's frictionless, you're doing the same amount.
Just
You're
less
saying
force.
more because
Distance.
the distance is more.
But
It's
less
but it's
force.
less force
You're
over
saying-
the same less force over a greater distance.
You're exerting
So it's
less
the same.
force, but you're exerting it over a greater distance.
So it's the
I
same.
agree with Mac. Mac, I believe
Okay.
in you.
Thank you, Landon. I appreciate
I
that.
just need to do some math.
Let's do some math, maybe
Yeah.
settle the argument.
I second your opinion, Max.
Okay,
I already
now,
seconded it.
here's what you're gonna see also, that a whole bunch of things that we've studied so far are gonna get all kind of wrapped back up into some big ideas here. So, here's the fridge. How much force, how can I calculate the amount of force that I have to apply to get it up the magic frictionless ramp? What's this?
Force parallel.
Okay, Forrest scored in Australian rules football. Yes. Okay. All right. You've never seen Australian rules football, it's bizarre. Okay, basically it's like American football with no pads or helmets. So,
Way more fun.
Sounds like rugby.
Yeah.
oh, no. Rugby, you kind of stop and, you kind of have, no. These guys are full bore, kill each other kind of thing.
Oh,
without
yeah.
pads. Okay,
Do they make?
and they're the most rabid fans in the entire world. Seriously.
That is awesome.
Oh,
I've
go to
never heard
Australia and watch Australian rules football with Aussies that have been drinking for a while. Oh my God, you will fear for your own life.
Are they worse
Okay.
than Raiders fans?
Oh my God. Well, no, but now, Raider fans are just weird, okay? These are like good-natured guys that just like, rip off his head, he can't play without his head, rip off his head!
Good-natured guys.
Into the hype and just getting into it.
Oh no, actually it was never like, rip off his bloody head, mate, rip off his bloody head!
Very good-natured guys.
That chokes me up. Okay, so how do you calculate force parallel?
FG sine theta.
How about FG sine theta?
Yes.
Little action like that?
Oh.
So in this case, I would take 98 newtons times sine 30 degrees, and I would get 49 newtons.
Easy.
Okay? Easy. So that's the force that I would have to exert. Now that's the one that I'm going to count, because that's the force that's in the direction of motion, right? I don't care about gravity acting down, because that isn't the direction that I'm moving. I'm only going to worry about the 49 newtons. But I've got to apply the 49 newtons over 2 meters. 49 newtons times 2 meters, check my math, is, wait for it, change colors, 98 joules. So you actually do the exact same amount of work.
But it feels easier.
But yeah, now here's your trade-off, and this is how all simple machines work. You're trading force for distance, okay? That's it. Now, if you're going, man, I'm not even feeling 49 newtons, okay? I need to make that force less. So what can you do?
Decrease the.
Yeah, make that board even longer. Your force is going to become less, but distance is going to become greater. So it's still going to be the same amount of work. Now,
Little f, big D, and then big F, little d.
that's basically it. Now, in reality, what's going to be there? Friction. So instead of 49 newtons, realistically, you might actually have to exert like 56 newtons. So if you actually had to exert 56 newtons, you're actually going to do more work using the ramp than you do if you just lift it straight up. But your trade-off, 56 newtons, even with friction, is still less than the 98 newtons it would take to lift it straight up. So you actually do more work using the machine. Okay. Now, let's talk time. Okay? And let's talk power. So power is work done divided by, work is measured in joules. So power is joules per second, and usually that's referred to as watts. Okay?
Yes.
And usually that's just abbreviated uppercase W. So where have you seen watts in your household?
A light bulb.
Light bulbs, right? So what's brighter, a 40-watt bulb or an 80-watt bulb?
Oh.
80-watt bulb, right? Why? Yeah, if you have an 80-watt bulb, it's 80 joules per second. If you have a 40-watt bulb, it's 40 joules per second. So the higher the wattage, the more energy is being produced per unit of time. Okay? There you have it. Now, let's look at this. So let's say that we're going to go back to the fridge, okay? And here's the tailgate. I'm going to lift it up. And let's say that I do it, and it takes me 10 seconds because I'm old, okay? So reach down, grab a hold of it, get time, okay? It takes me 10 seconds. So how much power was required for me to lift a 98 Newton refrigerator up to a height of 1 meter in 10 seconds?
9.8, yeah, 9.8 watts.
9.8 watts, right? Because I would take 98 times 1, I get about 98 joules. So I got 98 joules, divide that by 10 seconds, and I would get 9.8 watts, right? Now, Bree's there, she goes, Mr. Brookhamp, please allow me. Okay. So, Bree grabs a hold of it, and she lifts it up, and she does it in 1 second. Okay? Is she still going to do the same amount of work?
Yes.
She's going to do the same amount of work because she's going to lift it up to a height of 1 meter. But instead of dividing by 10 seconds, we're going to divide by 1. So what's going to happen to the power for Bree to do that?
It's gonna go up.
Increase the.
Yeah, so Bree is going to have to use a lot more power than I will because she's doing the same work in
Less time.
less time. Okay? Same work, less time, more power. Now, here's the other thing that you can do with this in case you ever buy an electric car. So power is work divided by time. Well, power is force times distance over time. Well, what's distance divided by time? Velocity. So that's also force times velocity. So if you ever buy an electric car, where's the power stored? Batteries, right? Power's stored in the batteries. Can batteries store an unlimited amount of power?
No.
No. You could, you'd never have to recharge your phones.
Yeah.
Okay?
I would.
Why not? So you have a certain amount of power. So if you ever buy an electric car, you need to be keenly aware of this equation. Because the faster you drive your car, number one, the V is going to become bigger. The faster you drive also, your frictional force becomes greater because you have more collisions with nitrogen and oxygen molecules. You increase that friction force. So if you ever drive a car, an electric car, you need to keep in the back of your mind this equation. Because the faster you drive it, that's going to require more force, which is going to drain that power faster. Now, even if you're driving relatively slow, let's say you're driving down to Oklahoma and you're driving the speed limit, but you're driving into a strong south wind. Okay, so you drive to Oklahoma, you've got a strong south wind. What's going to happen to the force? It's going to increase, so your power consumption is going to go way up. Okay. Now, if you're driving down there, but you have a strong north wind pushing you, then your force is going to become less because it's pushing you, and then you're going to use less power out of your batteries. So that's, I'm just telling you, if you ever own an electric car, keep this equation in mind. Okay? Good? Okay, stop that from setup again. So let me talk about number 8. So in number 8, here's the situation. You've got a bucket, right? And buckets, cranes that only lift empty buckets don't sell very well. It's like, what does your crane do? It lifts an empty bucket. Okay, cool. Nice. Probably will sell very well. So within the bucket, there is dirt. Dirt has a certain density. Now, for those of you that might need a quick refresher on density, we write it a little bit different in physics because we go rho is mass divided by volume. Rho just means density. In probably any other science class, you've seen it written as density is mass divided by volume. But in physics, we use the Greek letter rho. The other thing that's different in chemistry, because we're dealing in smaller quantities, this is typically like grams per cubic meter or grams per milliliter if it's a liquid. In physics, because we deal with bigger quantities, this is going to be kilograms per cubic meter. Okay? So if you look on that number 8, okay, you got 1.15 cubic meters of soil. Is that the volume, the mass, or the density?
Volume.
That's your volume. That's how much dirt that you've got. So you've got the volume that I gave you. You also have the density of the dirt. So what can you find? Mass of the dirt. Now, what do you think you're going to need to do to mass the dirt to do the work calculation?
Find the force.
Perhaps multiply it by
9.8 meters.
9.8 meters per second squared to get the
Gravitational force.
Yeah, or the weight of the dirt. Now, but what are you going to do with the weight of the dirt? Because what else has to be lifted?
The bucket.
The bucket itself. So here's what you want to do. You want to find the weight of the dirt, add that to the weight of the bucket, multiply that by how high it gets lifted there's the work that's done. Okay? So, just brief introduction on that. Now, when you get to question number 9, let me kind of give you a visual on problem number 9. I want to use rubber stopper, but it's the same idea. So, imagine that I'm dragging this rubber stopper along like this. Okay? So, if I drag this rubber stopper along like this, what are the forces that are acting on that rubber stopper? So if I said, okay, here's the rubber stopper. What are the forces acting on that rubber stopper as I'm pulling it? Which direction is friction going to act? Opposite direction. So I got some force friction going this way. What else?
Force gravity,
Gravity's pulling it down.
which means you have force normal.
Okay? I got some normal force, right? Have to have the table, right? Because if I pull the table up, okay.
Your
Does the
applied
string act
force.
as a force normal as well?
Huh?
Does the string act as a force normal as
We'll
well?
get to that. So, let's just call this the tension from the string, right? Okay, because that's applying the force. But what do you think that I can do with this tension? Break that up into what?
This and this.
X and Y components, right? So I've got some tension going in the X direction, and I've got some tension going in the Y direction, right? So what do you think the relationship is between this horizontal tension here and that force friction over there?
They're probably equal
Balance.
and opposite.
Balance. Now, if I ask you to do the work calculations for dragging this rubber stopper, out of 1, 2, 3, 4, 5, 6, out of 6 forces, what's the only one that I'm going to use in my calculation of work in dragging this rubber stopper like this? What's the only one I'm going to use?
T max.
Tx. Why?
Because it's going in the direction of motion.
You only do the force that's in the direction of motion. Okay? So, in terms of a work calculation, that's the only one I'm going to use. Now, when you get to question number 9, what I've given you is I've given you this. Okay? I've given you this 462 newtons. Okay? That's this number. The first thing I want you to find is the tension. Now, is your tension going to be bigger or smaller than 462?
Bigger.
Bigger. Why?
Hypotenuse.
It's the hypotenuse. So you know your tension has to be bigger than 462. Okay? Otherwise, you violated both Euclidean and non-Euclidean geometry, which is kind of cool. Okay? So keep that in mind. All right, I'm done. You're on your own.